So thus far in the course, we've discussed both differentiation and integration of various types of functions, but what we haven't done a ton of is differentiating and integrating with some of the more complicated transcendental functions. Functions like the natural log or logarithmic functions or exponential functions, or even any inverse trigonometric functions for that matter. So that's going to be the point of emphasis in this unit, actually going through the different transcendental functions and doing the calculus of those. And want to start with the natural log function, honestly, because it's the easiest. So let's start with discussing the derivative of the natural log function. And I'm not going to go through a rigorous proof of this right now. You can just go to my AP Calculus playlist, and I'll see if I can include a link in the description below. But I have a proof for the natural log derivative, so watch that if you're interested. But just kind of intuitively on a graphical level, if we wanted to find the derivative of the natural log function, there are a couple of ways graphically that we could do this. So one way is to just simply look at the derivative of our natural log function. And this is the natural log function here. You'll notice this is exactly the derivative of this is the natural log function. And if I wanted to kind of get a sense of what's happening with the derivative of the natural log function, I could just start approximating the slopes of the tangent lines at various points. So for example, at the point 1, what would that tangent line look like? Let me actually see if I can go in a little bit closer. Well, that tangent line would look something like this. And we can say that m is equal to 1 here. Well, what about at 2? What would that tangent line look like? And I should be able to sketch something like this. M is equal to 1 over 2, about 1/2. And if I wanted to keep going at 3, we can do something like this here. And we see that m is equal to 1/3. And do we notice any relationship between these points? 1 and 1, 2, 1/2, 3 and 1/3. And you might be seeing, yeah, clearly it just looks like it's the reciprocal here. That is to say, the derivative of the natural log function every single time appears to just be 1 over whatever your x value is. And that's not really a proof by any means. It's just something that I would hope that you would observe. Additionally, we could also look at, for example, something like the natural log function. So I'm just going to go ahead and graph that here. So let's take the natural log of x. And what some mathematicians realized is that there was a pretty cool relationship between the natural log function and the following integral. We can say, let me just do this here. We're looking at the integral from 1 to x of the function 1 over some other variable. Let's just call that t. And let's write this dt. And what we notice here is that, look, the integral of 1 over some argument, dt, is exactly the same as the natural log of x. And again, these aren't rigorous proofs by any means, but clearly there is a graphical relationship here between the natural log function and simply 1 over x. So again, watch if you would like to see a more rigorous proof of this, but for now, we can essentially establish the following. We can say that the derivative of the natural log of x is simply equal to 1 over x dx, okay? Or 1 over x for now. Now, that by itself is a little bit misleading because this makes it seem like the derivative is always going to be 1 over your argument x, and that's not entirely true. What's actually probably more accurate is to write this as the derivative of the natural log, let u be equal to some function. Let's let u be equal to some function. So we can then say the derivative of u is going to be equal to u prime, the derivative of u, all of that over the original function, u. Or we can write this as f prime of x over f of x. So that's the main thing to really think about, that the derivative of a natural log function is the derivative of that argument, of that natural log function, divided by the argument itself. So what does that mean? So let's try a problem here such as this. We would say to find f prime of x, or the derivative of this natural log, it would be the derivative of our argument here. We can, if we need to, we can even redefine this as u is equal to 3x squared. So we would say u prime, or du, is equal to 6x. We could write dx, but for now we can just write this as f prime of x would be 6x, this is my u prime, all of this over my u, which is 3x squared. And we could easily simplify that to just 2 over x, and that's it. Okay? Let's try another one. Let's try something like number 2 here. For number 2, we're going to treat all of this here as our u. So what is u prime? Well, if we're thinking about this in using our quotient rule, we can write this as 8x times the derivative of the denominator. Well, let me actually make some space here. You can just write this as u prime is equal to the derivative of my numerator, which is 8x, times our denominator, x minus 1, minus our numerator, 4x squared, times the derivative of our denominator, which is 1, all of this over x minus 1 squared. And then I could divide all of this by u here, whatever u is, which was 4x squared minus x minus 1, or divided by x minus 1. Now that looks a little bit gnarly, so I'm going to remove that for a second, and then ask yourself, is there another way that I could have done this? And the answer, hopefully you saw, is that absolutely. If I actually use my logarithmic properties and rewrote this as the natural log of 4x squared minus the natural log of x minus 1. Remember the log property that says ln of a over b is equal to natural log of a minus the natural log of b. This is a logarithmic property. If that's the case, this becomes so much easier. What is the derivative of my argument here? That's just 8x over my original function, 4x squared, or my original argument. Here, what's the derivative of x minus 1? Well, that's just 1 over my original argument, x minus 1. So we can say y prime is equal to this. Okay, and if you wanted to rewrite this or just compare your answer with having done the quotient rule originally, you would get x minus 2 over x times x minus 1. Okay, that's number 2 there. All right, let's compare that with number 3 over here. Let me just get that number 3. Now, there's a little bit of a typo here. I apologize. That's one of the reasons why I wanted to go over this. Those parentheses are missing. And without those parentheses, then you would be tempted to think that it would be natural log of 3t squared minus 5t. And you'd be correct. So that's why we need those parentheses. So if that is the case, f prime of x is equal to, what is the derivative of my argument, or the derivative of u? That'd be 6t minus 5. What is my original argument? 3t squared minus 5t. Okay. Let's go ahead and try another one. Let's try something like number 4 here. For number 4, we have to apply the product rule. So y prime is equal to the derivative of x, which is 1, times ln of x, or natural log of x, plus x times the derivative of the natural log of x, which is just 1 over x. So all of this just comes out to the natural log of x plus 1. Okay. Let me go ahead and just jump to something like number 8. I think this is a good one to discuss. So for this one here, you might be looking at this and thinking, we haven't really discussed how to find the derivative of an exponential function. How would I differentiate something like 3x to the x power? And I would say just sit tight, we will cover that shortly. But for now, is there any other way that I could evaluate this without necessarily knowing how to find the derivative of an exponential function? And the answer is yes, we can use our log properties. First off, we can rewrite this as, if we remember, I should say, that the natural log of a times b is equal to the natural log of a plus the natural log of b. So using that bit of information, we can write this as the natural log of 3 plus the natural log of x to the x power. And if that's the case, we can then further rewrite this as x times the natural log of x, which we can just move here. Well, x times the natural log of x, we already did that right above. We know that the derivative now of the natural log of 3, okay, let me jump to this part first since I was already on that train. The derivative of x times natural log of x is the natural log of x plus 1. And we all know that the natural log of 3, that's just some constant. So the derivative of any constant is 0. So y prime is actually equal to the natural log of x plus 1. Okay. All right. Let me just finish off this lesson by talking about the logarithms of other bases. So all the differentiating we've done so far has only been with the natural log. What about when your logarithm has a different base, like 10 or any other number for that matter? How would we differentiate something like log base b of x? Well, the key to this is understanding the change of base formula, right? So we can just simply remember that log base b of x using the change of base formula is equal to log of x over the log of b, okay? Which we can also write as a natural log of x over the natural log of b. The change of base formula says it doesn't really matter what your base is in the numerator and denominator. As long as those bases of my logarithms are the same base, it doesn't matter. We can still rewrite this as a logarithm of x over any logarithm of any base over b, as long as those bases are the same. So if that's the case, then we can rewrite the derivative of the log base b of x as the derivative of the natural log of x over the natural log of b. Now, think about this for a second. Ask yourself, how could I rewrite this? We can say, let me just move this over here. We can rewrite this, the natural log, or the derivative of the natural log of x over the natural log of b. This statement here is equal to the following. 1 over the natural log of b times the natural log of x. All I'm doing is taking that denominator and rewriting it as a factor. Well, remember, just like we saw in our previous problem, this is some constant. This is simply some constant, since e is a constant. So we can effectively factor this out. When we're taking the derivative of some constant times some function, this is equal to 1 over the natural log of b times the derivative of the natural log of x. And I think this is really cool. All this effectively does is it allows us now to use the same understanding that we have of taking the derivative of the natural log function. So this we've already discussed. We know that's simply going to be x prime over x, or u prime over u, or f prime of x over f of x. The derivative of your argument over the argument itself. Then we just simply need to multiply it by 1 over the natural log of your argument, which is what we have here. So this is just another way of rewriting this here. But the main thing for us to remember is, let me just kind of box this. It doesn't really matter how we write it as long as we understand. It's to find the derivative of any logarithmic function. It is simply 1 over the natural log of that base times the derivative of your argument, or the derivative of the natural log of your argument. So let's do an example of this right now. Okay. So let's say, for example, let's do this one here. Okay, and this is going to be initially a little bit challenging, but I think it'll make a lot of sense if we can use some log properties. So I'm going to rewrite this using log properties as the following. Well, actually, let me just do the derivative first, and then we can apply some log properties. So we've got y prime. We're going to write this as 1 over the natural log of our base, so the natural log of 3, times the derivative of the natural log of our same argument. Okay, so now that we've set this up, so now we can say this is equivalent to 1 over the natural log of 3 times the derivative, and I'm going to expand this using our logarithmic properties. Which then allows me to rewrite it as the following. Let's go ahead and differentiate each term. The derivative of natural log of x is 1 over x. The derivative of the natural log of root x plus 1 is 1 over 2 times x plus 1. The derivative of any constant, which natural log of 2 is 0. And then I can simplify this nicely to the following. This would just be 3x plus 2, all of this over 2x squared plus 2x. Okay? All right, so hopefully this helps give an understanding of how to find the derivative of natural log functions and logarithms of any other base.